Hello everyone, welcome to the OneClass channel and good morning. My name is Fejiro and I'm an honors Bachelor of Science student working towards med school. Today we'll be going over some commonly asked chemistry questions. The chemistry questions are both at the high school and college level. If you need some extra help with your homework or tutoring, for example, you can definitely check out the links in the description below. Okay, so with that being said, we can kick it off, get started on this session here with the first question. Let's see what we have. Okay, so this question is asking us to calculate the mass of an atom. Okay, of helium. Actually, let me just put it as they did. Helium, iron, lead. Okay, and the atomic masses for these atoms are 55.9, so 4.00 units, 55.9 units, and 207 units respectively. Okay, so then how do we solve this question? Okay, we would actually go over to our conversion table. I believe it's this one here. When you see here physical constants, they want the mass of an atom. Sorry, I can do that better. They want the mass of an atom. Okay, do they specify? And it said the answer is in kilograms. In kilograms. Okay, so the good news right here actually is that we have a conversion factor that we can use. Okay, so with that being said, okay, we would treat it as, kind of like the conversion questions, where we want to put what we have opposite of each other so that they can cancel all the units, and what we want on the same level, as in, like, if what we have is in the numerator, what we want should also be in the numerator, and what we have should be in the denominator. Let me show you with an example. For this, we have 4.00 units for helium, right? If we wanted to find out the mass in, grams first, we would say 1 unit down here and 1.6605. I'm going to write the whole number, just going to do that, and then times 10 to the negative 24 grams. Okay, but they want kilograms, and we do the same exact thing. We know that there's 1,000 grams in 1 kilogram. So now watch this. These units will cancel out, these units will cancel out, and then what you get is a value you have to put in the calculator. So 4.00, okay, times 1.6605 0, okay, to the power of negative 24, okay, divided by 1,000. Okay, so what we get as a total for the helium one is 6.6. Let's make it the same amount of significant digits. Since they gave us 3 for the 4, we have 6.64 times 10 to a negative 27 kilograms for 4 atomic mass units of helium. Okay, so now we do the same exact thing, but this time with the iron value, the 55.9. Okay, so it'd be the same thing, 1.6605 times 10 to the negative 24 grams equals 1 atomic mass unit, and then 1 kilogram is equal to 1,000 grams. And now let's see what we get for that one. Okay, we get, let's see, 55.9 We get a slightly larger number, which makes sense because we do have a larger amount of atomic mass units. We get 9.28 times 10 to a negative 26 kilograms. Okay, and if we're going to follow this trend, most likely the lead is going to be at least 10 to a negative 25 kilograms. But let's see here if that's actually the case. So we have 207 units, okay, times a 1.6605 times 10 to a negative 24 grams, okay, is 1 unit. Oops, sorry. Always remember to put your units so you actually know what you're canceling. So I'm just checking back my previous work. And then 1 kilogram is equal to 1,000 grams. The grams cancel, the atomic mass units cancel, and now we have a 207. Okay, and yeah, for this answer we have 3.44 to round it properly times 10 to the negative 25 kilograms. So as you can see, when they're weighed in just atomic mass units, it's a very small amount, well, in terms of grams and kilograms. So let's see how we did for this question. Let's see how they solved it. By definition, yep, they do have the conversion factor. It is 1.66 times 10 to the negative 24. And they do explain how we get that number, actually. They use kind of like the atomic mass units for carbon times 12. So like you want to have like the carbon 12 and then divide that by the 6.022 times 10 to the negative 23rd. And that's how they get their conversion from the atomic mass units to grams, because most things are kind of based on the carbon 12 isotope. So now, as they did here, exactly, they have the 4 units times 1.66 times 10 to the negative 24 divided by 1,000, which is what we did, and we get, yep, 6.64 times 10 to the negative 27. For the first one, 9.28 times 10 to the negative 26, and 3.44 times 10 to the negative 25. So with that being said, this is correct. Alright, so definitely a great start. We can move on now to question 2. So this question is asking, what is the molar mass of nitrogen dioxide? NO2, okay? And how many moles of NO2 are present in 114.95 grams? Okay, so 2-part question here. I'm actually going to add a third question. Notice how when I said NO2, I said nitrogen dioxide. Okay, why is that? Well, if you look at it, NO2, right? This is a type of covalent compound because there's 2 non-metals together. And when you have 2 non-metals together, okay, the way the naming works is that you have to make sure you assign the appropriate prefixes to them. So oxygen here has 2, as you can see. So because of that, okay, where you're gonna have to specify when it comes to covalent compounds that 2 oxygens, where you should use di. Hence why the name is nitrogen dioxide. Okay, so that's just a little fun fact there. Now this question is asking how many moles of nitrogen dioxide are present in a, whoops, that's the second question. They're asking first for the molar mass of NO2. So for this, we solve it first by getting its constituents. So we have 1 nitrogen, 2 oxygen, okay? And now if we look at the periodic table, okay, nitrogen weighs 14.007 atomic mass units. Oxygen is 15.999. Okay, so we would make that, we would do the whole process of the multiplication, 31.998, and then we add them together. Okay, and the answer we get here is 46.005. Okay, and that is grams per mole. So with this, we now have the molar mass of nitrogen dioxide. Now it's asking us how many moles are present in this amount of grams. So for this, kind of like how we were doing the conversion for the earlier question, we want to make sure that we're converting properly. So they've given us 114.95 grams of NO2. Okay, so now that we have this formula here, we want to make sure that we put the right things in the right place. So we would actually put the 46.005 grams of NO2 at the bottom is equal to 1 mole of NO2 at the top. Okay, and when we do that, we're pretty much having to divide the 114.95 by our molar mass, because you'll see the units definitely cancel out. 95 divided by that, and we get 2.4, and we want to keep the same significant digits around there. And because this one had 5 in total, let's try to keep 5. So 1, 2, 3, 4, 5. Okay, 2.4986 moles of NO2. That's the amount of moles there present in 114.95 grams of nitrogen dioxide. So with that being said, let's see how we did for this question. Okay, so the mass of 1 mole of nitrogen dioxide is, yep, they definitely got the 46.005. Alright, and now for the number of moles present in 114.95, exactly, they get the 2.4986, which they did round up to 2.5. So with that, this question is also correct. Okay, so nice, we're so far 2 for 2. Let's move on to question 3. How do you convert grams to moles and moles to grams? Great question. We actually just touched upon it in the previous question. So how to convert grams to moles and moles to grams. So like I said, you want to make sure that because you start with grams in the numerator, you want the for it to cancel out, you want to put the grams per mole, like you want to put that inverted. You want to put the grams there in the denominator to make sure that you're canceling out your grams, your units, and then that way you have only moles left, and vice versa as well. So as an example, right, I'm not going to use any actual values. I'm going to say that an element has A grams per mole, okay, and the element has X grams, okay. So we don't know how many grams, we don't know exactly this number, but this would just be kind of the steps you take to make sure that you do solve it properly, okay. So let's start with a question where we try to convert grams to moles. Okay, so we start with X grams, okay, of element, and what we want to do to make sure that it does cancel out is that you want the grams part in the denominator. So it'll be A grams is equal to 1 mole of the element. Okay, so in reality, these are coefficient, these numbers, right? It would pretty much would be x over a mole. Okay, that would be able to really solve you any question that involves converting from grams to moles. Now you're probably wondering, how do you get now from moles to grams? Okay, so let's say you had y moles. Okay, so here we do the same thing. We have y moles of an element. Okay, but this time you want the moles to cancel out to get to the grams. So now the 1 mole would be at the bottom, okay, to make sure you cancel out, and the a grams would be at the top. So when you actually did the math here, okay, it would actually end up being y times a grams of the I guess molecule in question. So you see these moles cancel out in the first question, and the second question, and the previous question, the grams cancel out. Take any value really, and you have to work through that. So let's say, for example, we're working with hydrogen, right? And we know the molar mass is 2.016 grams per mole. If I said I had 1 gram of that, it would be 1 divided by 2.016, and that would be the moles. So in that example, it would be that we had around 0.5 moles of hydrogen. Okay, now funny enough, if we took that 0.5 moles of hydrogen, right, and then we use it as a y, and then we multiplied it by, the 2.016, which is still the molar mass, okay, you would end up getting back to the original question, to where now it would say we had 1 gram of hydrogen, H2. And so that is how these would convert, and it's pretty cool because if you kind of put it all together and you made them equal each other, you would notice that ya is equal to x, and and y is equal to x over a. See how they relate? You really just move the a to the other side, and you divide both sides by a, okay? Because the relationship is, if you kind of drew that triangle, not sure if you guys remember, but it would be that the grams would be at the top, okay, x, the moles would be on the side, y, and a would be the molar mass. So then whichever one you're solving for, you would then in a sense work through the other one. So for example, if you wanted the molar mass, it would be x over y. It's kind of like that. If you wanted the moles, it would be x over a. And then if you wanted the grams, it'd be y times a. So this is kind of like the relationship triangle here. If you were ever confused, hopefully we kind of addressed the whole situation of how to convert between each other. So yeah, let's see how they did. They talk about exactly the grams are canceling out, and then they do the same thing here where they converted back, and you notice that there's still, you start with 25 grams, you end up with 25 grams, because exactly that's what you should be ending up with. Okay, so this is correct. I think the point to emphasize here is that when you are solving for like grams, moles, and stuff, when you convert back without making any changes to the grams and the moles, you should end up with the same value for the grams and moles. That you will not see any loss of, I guess, product when you keep converting back and forth. Okay. So let's move on to question 4 now. Okay. Why is O2 a molecule? Wow, that is a very intense question. Why is O2 a molecule? So, O2 is not just a molecule, but a specific type of molecule called an molecular element. So why do we call it this? Okay, so now there are different types of I guess different classifications. So with this, okay, if we were to picture O2, right, it is two oxygens kind of just bonded like that, okay, and that's how they float in the atmosphere, okay? That's oxygen that we breathe. So there's three different types of definitions we have to familiarize ourselves with. We have just an individual element, or we just call them like yeah, an individual element would be what we will call it here. Okay, and we have then a molecular element, and then we have a molecular compound. Okay, so to describe each three, an individual element is just like an element by itself. Okay, those are things like most of the metals on the periodic table, or even the noble gases that don't bond with anything. So like neon, calcium, these are what we consider individual elements which exist in nature just literally by itself. Okay, as in like it doesn't need to be stabilized by bonding to anything else. A molecular compound is like, let's say we have the perfect example, H2O, where we have two hydrogens and one oxygen. That is a molecular compound because it is two. Oops, I actually prefer to do this. So exactly, so we have that oxygen there, and then we have the two hydrogens attached to it. Okay, that is what we call a molecular compound because it's made up of different elements. Okay, now the last one we're addressing is molecular elements because, as you can guess, it is still made up of, you know, multiple things, but it's a multiple of the same. Hence why it still has the name element in it, because it's multiple of the same element. Now, to tie it back to the question of why O2 is a molecule, okay, the reason being is because although it is the same element bonded together with itself, as soon as you have more than one element, it becomes a molecule. That is just the definition of molecules. So like even if you saw something like O3, which is like usually in the ozone, this right here is still going to be a molecule, okay? Because even though it has 3 oxygens, it's still constituted of more than one element, okay? The things really that don't count as elements are these right here, things that just go on by itself. So things that don't count as molecules, okay? So things like neon, sodium, potassium, things like that just are by itself, those do not count as molecules. So this is why O2 is a molecule, because it's more than one element in there. Okay? So exactly, molecules are defined as 2 or more atoms bonded together. Oh, that's a better word. Not individual element, but atomic element. Okay? And then there's molecular element and the molecular compound. Exactly. Diatomic oxygen means that there's 2 atoms of oxygen, and these are bonded together. So using that definition of molecule, O2, even N2, fluorine that floats in the air, like most gases actually from like the halogen group, are usually going to be molecular elements because they're usually bonded like 2 like that. So with that being said, this is correct. Okay, and that was one of question 5. What are the main properties of ionic compounds? Okay, so main properties of ionic compounds. Okay, so with this, actually, the first property I like to always point out is what they're actually made of. Ionic compounds, by definition, have to be a metal, okay, with non-metal. Okay, that is one of the properties that you should be looking at first glance. When you see a molecule, like, and the name and everything, you want to check if there's a metallic part and a non-metallic part. Okay, because that, in a sense, will tell you right away that's an ionic compound. So what comes with that? Because we have a metal bonded with a non-metal, it goes a little bit deeper than that, but the point being is that one of the properties is that they have, as you guessed it probably, ionic bonds. Okay, and this actually comes from the electronegativity, so that's actually what I wanted to discuss. So electronegativity is pretty much the electron affinity, how much it wants to have an electron, like take an electron from its surroundings. So you see here the metals, when you look at the electronegativity, okay, like sodium for example, it's quite low. Okay, we have 0.93, and then when we go ahead and try to bond it with something like fluorine, right, which has a high electronegativity, that's 3.98. So the range for ionic compounds usually start around at 2 electronegativity. Anything surpassing that, which this calcium fluorine or even like sodium fluorine does, like sodium fluorine, it's just going to be an ionic compound because it passes that 2.0 threshold. There are some ionic compounds that are more in like the 1.6, 1.8 thresholds, but it still counts ionic because it's still a metal with a non-metal. Okay, so what this electronegativity difference does is that if we took the example of the sodium fluoride, right, is that it would kind of look like this, where when you do the Lewis structure, the fluorine would actually just hog all the electrons, okay, to where it's more like this. You have just literally a positive side and a negative side, because the sodium has literally given its electron away. It's not like they're sharing it or anything. The fluorine has just taken it. So this is the type of bond that ionic forms. Now, with that being said, ionic bonds are the hardest type of bonds to break. Aside from like metallic bonds and stuff, and that one's a whole different discussion topic. But if we're going from like, non-polar, covalent, all the way to ionic bonds even surpass things like hydrogen bonds. So because they're the hardest bonds to break, ionic compounds are usually, okay, have the highest melting point / boiling point. Okay, because the fact that these bonds are really hard to break. Okay, and because as well, there's situations like that. Some of them have a very easy time dissolving in water because they have exactly a positive side and a negative side. But this is really the ones I want to emphasize. The properties of it is that it's a metal with a non-metal. They are composed of ionic bonds, which are the hardest bonds to break, and they usually have the highest melting / boiling point. But it just depends also on like the size of the molecular compound as well. Okay, so let's see what they say. Strong attractive force between a cation and anion. Yep, metal and non-metal. Metal is serving as the cation, and this is serving as an anion. Okay. Strong refracting point, which is high melting and boiling point. And I'm not sure about this part, but there's something else I guess you need to know as well, that high enthalpies of fusion. So exactly, like, to actually form them, you need quite a bit of energy. And ionic compounds are also hard brittle, so it's kind of like you'll see a lot of them like in powders or like you know, like in kind of like crystallized structures. That's usually what we see for ionic compounds. An example would be like salt, for example, NaCl. And exactly, it dissolves typically, and they're electrically charged because exactly we have a cation here. Hence why it dissolves like in water, for example, because it has has a polar and non-polar sides. I mean, has a positively charged and a negatively charged side. So the sodium would go towards a negatively charged side, which is the oxygen in H2O, and the fluorine would go towards a positively charged side, which is a hydrogen in H2O. Okay, so yeah, these are just really all the main properties of ionic compounds. And with that being said, I think the ones you need to highlight to differentiate from the other compounds, like the covalent compounds, you want to make sure that you are identifying that you have a metal and a non-metal. Sorry. You want to understand also that if you're going to list out a bunch of compounds, usually the ionic compounds are the hardest bonds to break, and exactly they usually have the highest melting / boiling point. Okay. All right, let's move on to question 6. Is beryllium chloride polar? So, is beryllium chloride polar? So the reason why I call it beryllium chloride, as you notice, right, this is an example of an ionic compound, and because of that, the naming rules, right, we don't state, okay, like we not even need to, we actually do not state the fact that there's 2 chlorines there. We don't say beryllium dichloride, we just say beryllium chloride because it's a metal with a non-metal. And the question is asking if beryllium chloride is polar. With this, the best way to start, usually just drawing a Lewis Lewis diagram or Lewis body diagram or body dot a Lewis diagram. There we go. So the way to draw it is that we need to first figure out how many valence electrons are in beryllium and in chlorine. So for beryllium, because it's on the second column, we can say it has 2 valence electrons, but we can actually figure this out as well by drawing quickly something that we've been reviewing a lot lately, the electron configuration, which would actually start with helium, okay, and just be 2s2. So you can see here, because it has a 2 here at the top as a superscript, that supports that is its valence electrons amount. So beryllium would like to just give it up to be 2 plus, okay. Well, I mean, sorry, we don't need to know that. We just know that it has 2 valence electrons we have to account for, okay. And chlorine, we're going to approach it the same way. Quickly do the, I mean, it is on the 17th column, which means it will most likely have 7 valence electrons. But we always like to double check. So let's start with neon, and it would be 3s2, 3p5, okay, because we have the 2 here, sodium, magnesium, and then we count from aluminum 1, 2, 3, 4, 5. So yes, indeed, we have 7 valence electrons. So now there's 7 times 2, that is 14 in total. So to account for the valence electrons, we need to account for 16 electrons total, okay? So for this, because typically what we want to do is that the atom or the element with the least amount usually kind of situated in the middle. So we have beryllium in the middle, right? And we know that at least there is a single bond indicated by 2 electrons to the chlorines, okay? And now we add the chlorines there, and then we just kind of fill in the shells. At least we assume, because beryllium only had 2, so it doesn't really care about getting the rest, and chlorine wants to follow with the octet rule, right? And we kind of just fill in blindly, but then we count to see if we actually coincidentally accounted for all of them. So we do have 2, 4, 6, 8, 10, 12, 14, 16. So we actually accounted for all the electrons that BCl2 should have beryllium chloride. So with that being said, now we just have to make sure that we actually did it correctly by factoring its the electron number. Okay, so with that being said, beryllium prefers to have 2 because that is its valence electrons. We subtract how many lone pairs it have, which is 0, minus how many electrons in bonds, divide that by 2. So we do get 0 indeed. So beryllium is nice and satisfied. Chlorine, on the other hand, okay, we have 2, 4, 6 valence electrons and just 2 electrons in a bond. So with that, we also get 0 plus. We also get 6 plus 2 over 2, 7. So 7 minus 7 is 0. So this is completely satisfied in terms of how it wants to situate itself. So now, because we see one bond, let's just redraw it. We have Cl, Be, Cl. So with this being said, actually, we have just an electron, we have a, I guess, bond number, electron bond number of 2, okay? And we have 0 lone pairs, at least on the beryllium, because that's what we're referring to. Not the chlorine, but the beryllium, the molecule in the middle, okay? So with that being said, this is going to be a linear, okay, linear electron geometry. And because of linear electron geometry, even though these two are indeed polar, as in these are the more, actually not even more electronegative, this is literally just, chlorines are the negatives, well, not negatives, but chlorines are where the I guess negative charge will be situated, because you see all the electrons there, okay? But they literally, in terms of electronegativity, are pulling themselves equally to both sides, making that although we have ionic bonds, which does give directionality, okay, because remember the metal and non-metal, even though we have ionic bonds and they're quite big, because it's going to be 3.16 minus 1.57, so 3.16 minus 1.57, 1.59, which, remember, when we look at it, it's still a metal and a non-metal, so even though it doesn't hit the threshold of 2, it does still check off as ionic, okay? But the point being is that the chlorines are kind of like, in a sense, a perfect tug of war, to where they're pulling at each other, but no one will ever win, making BeCl2 in total a non-polar molecule, because it has a net, I guess, pull or charge of 0. Okay, as in there's, as you see here in this picture, everything balances out, so this is a non-polar ionic molecule. Okay, so let's see how we did. Yep, it is non-polar, and the way they explain it, exactly, they're symmetrical, as we showed through the linear electron geometry. And so they're non-polar, and yeah. So you see how I broke it down by first, drawing the Lewis dot diagram. Sorry, that's because using this method, you can actually see clearly if beryllium had any lone pairs, which it doesn't, and you can also see how the electrons are kind of like, I guess, situated between the two elements on the outside, showing how they balance each other out in total. Okay, this is correct. So now we're 646, moving on to question 7. What do we have for question 7? What is the electron configuration for bromine? So now let's refer back to the periodic table. Okay, now I know that we typically use, at least when I've been using the shorthand, but for this we're actually going to we're actually going to use a longhand for this to kind of indicate why we use the shorthand. Okay, so for helium, let's start there, because we want to go, the way to do electron configuration is literally start from hydrogen and you count through, assigning the appropriate subshell to it. So for helium, we start all the way at 1 because it's in the first row, S2. That would be helium, okay? And now neon, okay, is that we would start at helium, so that's at 1s2. We can actually just replace it, and then you have 2 because now it's starting at the second row, 2s2, 2p6, okay. And then for argon, okay, and the reason why, actually I'll show you actually with an easier example, helium and neon. So helium, we have 1s2 because the first shell, the S1 is being filled, at least for the first row. So hydrogen, that would be 1s1. Helium would be 1s2. We move on to neon, okay. Then we go now down to 2s1, 2s2, 2p1 starting the boron, 2p2, 2p3, 2p4, 2p5, 2p6, okay. And then you probably guessed it, for argon we start now at 3s1, 3s2, and then 3p1, 3p2, 3p3, 3p4, 3p5, 3p6 on the argon, okay. So exactly would reflect that starting at the neon, okay, it would be 3s2, 3p6. Now let's go all the way to krypton. I know that it was asking for bromine, but krypton, okay, it's a little bit different. Exactly, start at argon, and then you do the same thing. It'll be 4s2, but you have to actually pass through this row as well. So now the way this row works, okay, is slightly different from I guess the other ones, right? So we're actually now with the D shell, that's the ones here starting at Scandium, it'd be 3d1. So you've actually gone back a shell and you start counting there. So 3d1, 3d2, 3d3, 3d4 on the chromium, 3d5 on the manganese, 3d6 on the iron, 3d7 on the cobalt, 3d8 on the nickel, 3d9 on the copper, and 3d10 on the zinc. So 3d10, and then you go back to counting as regular, where it would be 3p1, 3p2, 3p3, 3p4, 3p5 on the bromine, and 3p6 on the starting at the gallium, it would go back to the 4. So not 3 anymore, it would be 4 again. So it would be 4p1, 4p2, 4p3, 4p4 in selenium, 4p5 in bromine, and 4p6 on the krypton. But you actually would want to reorganize this to where you have the lowest shell number in front, which is indicated by the coefficient in front. So 3d10, 4s2, 4p6, okay. So that would be actually how you broke that down, okay. So in total, if you wanted to write down the whole thing from helium to krypton, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, okay. But for this question, they're asking for bromine, not krypton. So we did technically pass bromine, right? So remember that it was 4p5. So literally be exactly the same as we've written above here, but it would be not 4p6, it'd be 4p5. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p5, okay. And if you want to write down the shorthanded version, okay, it would be starting argon, as in the most recent, kind of like with the krypton, the most recent noble gas, and we just have to fill out the valence shell, and including also the D level as well. So the 3d10, 4s2, 4p5 would be the shorthanded version for bromine. Okay, now the reason why I broke it down like this is because I'm hoping you're seeing how I'm even getting the subshells and how I count them through using the periodic table. Okay, so this hydrogen and beryllium, well, columns 1 and 2 kind of as pretty much like the S shell, including helium, which is all the way over here, and then the columns 13 through 18, not including helium, are the P shell. Columns 3 to 12 refer to the D shell, and then the one we don't really address here, but the lanthanum and actinium series, that counts as the F shell. Okay, so yeah, let's see how we did. So exactly, technically this is correct, but also incorrect, because you still want to make sure that you're starting always with the lowest I guess electron shell number, which is the coefficient. So it should actually be 3d10 4s2 4p5. But yeah, so exactly, it's explaining how the periodic table fills out, and exactly it's telling you how each orbital has a certain amount of electrons. So after filling it out, they do have the 4s2 3d10 4p5. So that I would just reorganize that to make sure the 3d10 is in front. Okay, and this is actually a very fantastic picture showing the electron configuration. As you saw when we were solving for bromine, we had a 4s2 3d10 because it covered this whole D row, and then we went back to the 4s and we ended at 4p5. Okay, so this is correct, although it should be reorganized with lowest shell first. So it's gonna be argon 3d10 4s2 4p6. Okay, the reason why I keep emphasizing that is because some chemistry professors, teachers can be very specific to what they want, and you could lose marks if you have it in the wrong order. So now, with that being said, let's move to question 8, and it's asking us, what is the charge of the barium ion? Okay, so with this, actually, barium is all the way down here. Okay, as you can see, sorry, kind of an early morning for me. So with that being said, okay, to find out the charge of the barium ion, we can actually just refer straight to the periodic table. It is on the second column. Okay, so most likely it's going to have 2 valence electrons that it wants to get rid of to follow the octet rule, but we can actually show it a different way as well. So kind of like how we're doing the whole electron configuration, we can start from the most recent noble gas, which in this case would be xenon. Okay, kind of like we're doing just the electron configuration, the shorthanded version. Okay, and as we've discussed, right, it's 6 because it's in the 6th row, S because it's here in this corner here in the first and second column, 2 because it's the second one there. Okay, this tells us actually, because it has a 2 up there, that's the not the charge, but exactly has 2 valence electrons. So to become quote unquote a noble gas, instead of having to add 6 more to fill the octet rule, it'd be easy to just get rid of those 2 to fill the octet rule. So then typically then the charge of barium you'd see in nature as an ion would just be 2+, because when you get rid of electrons, it's a positive change, hence why we have 2+ right here, because it got rid of 2 electrons. Okay, so that would be the charge of a barium ion. Now, with that being said, let's see how we did in regards to this question. I was able to show 2 different ways. One just using the periodic table, the next way just actually showing the electron configuration. Okay, so actually electron configuration is actually what they use here in this question, and it is 6s2, which means it has 2 valence electrons, and then it gives us that 2 to fill the octet rule rather than trying to gain 6 more. Therefore, exactly, this charge is 2 plus. This is correct. So exactly, this is a barium 2 plus ion. So now question 9, okay? Why is ammonia considered a base? Whoops. Why is ammonia considered a base? So actually, for this, because ammonia almost has no relation between name and compound, you just have to kind of memorize it, okay? And I'm sure you've seen ammonia quite a bit in terms of like when it's written, okay? Ammonia is specifically NH3. That, let me just write that better. That was bothering me. The end didn't connect. Oh my gosh. Oh well. So NH3, okay? That is ammonia, right? Now to figure out why it's a base, okay, we want to be able to write it actually in its Lewis dot diagram, because that way we can actually see how it classifies as an acid or a base. But this question is supporting that it's most likely going to be a base, and I'll show you why, okay? So nitrogen, not only is it in the 15th column, okay, but when you also do its electron configuration, you'll see that you start first with helium, okay, and then for this valence shell it'd be 2s2 2p3, okay, indicating it has 5 valence electrons. Hydrogen, funny enough, is literally just going to be 1s1, so there's 1 valence electron for every hydrogen, so it'll be 1 times 3 and 5, so we have to in total account for 8 electrons, okay? And so for the Lewis dot diagram, let's just put the nitrogen because it's the least in the middle, and it's going to be bonded to 3 hydrogens like that, okay? And now for the last one, actually, we have to fill the shell. So nitrogen fulfills the octet rule, and hydrogen is completely fine with just 1 bond. And if we did the electron number to find that electron number, right, it'd be same, that 5 valence electrons minus how many lone pairs it has, which is 2 electrons in its lone pairs, plus the amount is sharing in its bond, so it'd be 6 divided by 2. So 2 plus 6 over 2, that's 3, so that's 2 plus 5. So exactly, nitrogen is satisfied, and the hydrogen, 1 minus 0 plus 2 over 2, okay, that is 1 minus 1, we got 0 as well. So this is completely how it wants to be. So now, what do you notice right away? That NH3 has a lone pair, okay? So the definition of a Bronsted-Lowry base, okay, is that it has a lone pair that it can use to attack and take a hydrogen. So what happens here is that as there's I guess not even just a hydrogen, specifically a proton. So as there's H plus, quote unquote, floating in the water, this lone pair will actually attack this to where you would now have, because there's also a positive charge in that H, okay, it would attack it to where now we have this, okay, with the positive, near the middle to account for it. Considering now that, if we redid the number, it would be now 5 minus 0 lone pairs minus 8 over 2, okay, it was plus 8 over 2, so that's 5 minus 4, which is 1, hence why we have the positive charge on the nitrogen. So that was what we get when that lone pair attacks that hydrogen. Now you're probably wondering, why would it want to go from a stable 0 to a positive charge? Its summary really is because of how much hydrogen bonds play a role in it. Hydrogen bonds are so powerful that in terms of like the cost and loss of energy, is that nitrogen is willing to give up that charge to be able to make sure that it has as many hydrogen bonds as possible when it comes to at least ammonia reacting with excess protons in a system. Okay, so if we were to, so now we've shown that in a sense with the Bronsted-Lowry definition of a base is that because it has a lone pair, it's able to take a hydrogen. And remember, bases accept hydrogens, which makes this, okay, a base. Okay, that's why ammonia is considered a base. And if you're actually to write down the whole formula to where it was attacking, forming that H+, it'd be kind of like this: NH3 plus, let's say, water, right? Because that's an example as well of a double bond as well that it wants to kind of tackle. I mean, not double bond, a hydrogen bond, which is why it's quite competitive. So that nitrogen will try to, in a sense, attack one of the hydrogens on the oxygen. Okay, and so now we have NH4 plus OH minus. Okay, so as the rules as well state, we have this one that received the hydrogen, so this will be the conjugate acid, and this one would be the base. Okay, and in this case water lost a hydrogen, so this would be the conjugate base. Okay, and this would be the acid. So in both explanations, the NH3 still serves as a base. So that's why in total ammonia is considered a base. And now you're probably wondering, oh, can't ammonia give away any of the other hydrogens? So here's where in a sense why it can't. As I've shown you, this NH3, right, it really likes its hydrogen bonds, okay, and it wants to have as many as possible, but within keeping its electron number. If I got rid of a hydrogen, so if we for some reason had NH2 minus, right, okay, not only now does it, like, it will be shown like this, it'll be 2, it'd be like that, and there would be a minus on the nitrogen. Not only would it have less hydrogen bonds, which it personally doesn't like, it's even its electron number, if you did the math, it'd be 5 minus 4 now, because there's 4 electrons in this lone pair, plus 4 over 2. So it'd be 5 minus 6. So it'd be minus 1, okay? So now it's lost a hydrogen and is also off balance in regards to its charge. It really gained literally nothing. So it would never, or rarely actually, want to give up a hydrogen to, form NH2 minus, okay? Because it just doesn't gain anything. Here, when it goes to the NH4 plus, right, at least it got an extra hydrogen bond to make up for the fact that its charge is now no longer 0. It wants to get as close to 0, right? But now when it comes to NH2, it's now no longer 0 and there's less hydrogen, so it really lost in every sense. Hence why ammonia would not be giving up its other 3 hydrogens there. Okay, so exactly, we have here Bronsted-Lowry base accepting the proton, which is what we have, and so it forms a new species called the conjugate acid in this case for the ammonia, and exactly because it reacts with water to form NH4 plus, hence it's a base in all accounts. Okay, so this is correct. So now let's go on to question 10. Explain why CHCl3 is polar but CCl4 is not. Okay, so explain why CHCl3 is polar and CCl4 is not. Why? Okay, so for this one exactly, we'd actually have to draw our Lewis dot diagrams for both to explain it. So let's head over now to the periodic table. Sorry about that. I have a little sniffles. So carbon is on the 14th column, or exactly if we drew it out using our electron configuration, just to be able to practice that, you will see why it has 4 valence electrons. So we have, starting with helium for the shorthand, 2s2, 2p2. That is how this has 4 valence electrons. Hydrogen, as we discussed, is still just 1s1, hence why it's 1 valence electron. And chlorine, okay, is going to be, starting at neon for the shorthand, 3s2, 3p5, because we've already covered the s rows from the first and second column, okay, and then we have now from the 13th to the 17th column p5, okay. So that's how it's 7 valence electrons. So now, with that being said, okay, let me just quickly clear my nose. This works. Okay, and we're back. Oh, okay, good. Because I was getting a little bit annoying to deal with, having to breathe through my mouth. So with that being said, okay, yes, back to the points. 7 valence electrons here. So now for CHCl3, okay, we want to account for in total 7 times 3, so that's 21. Okay, 1 electron here and 4 here. So if we add it all together, it'd be 26 valence electrons. Okay, and for the CCl4, right, kind of the same thing, because now we know that chlorine has 7, so it'd be 7 times 4, that'd be 28 plus 4, so it needs to account for 32 electrons. So it's not actually electrons that determine polarity, but it helps us draw our Lewis dot diagram. So starting with CHCl3, we want to put the carbon in the middle, because carbon is typically in the middle. Okay, and we have Cl, 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 H. Okay, and then we fill out the chlorine specifically because of the fact that they have more valence, so they need to account for it, more valence electrons. And then we see if we accounted for the right amount. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oops, I think I miscounted. 2, 4, 6, 8, 10, 12, 14, okay, 16, 18, 20, 22, 24, 26. So this does have 26 valence electrons, and if we quickly did the math for the electron number, it would be 4 minus 0 plus 8 over 4, since there's 8 electrons being in a bond. That does equal 0. For the hydrogen is 1 minus 0 plus 2 over 2. Same thing, it's also equal to 0. And now for the chlorine, it's 7 minus 6, because there's 6 electrons in the valence, in the lone pairs, plus only sharing 1 bond, so 6 plus 2 over 2, that's 7, so 0 as well. So this is perfectly how it wants to be. Using that information, really, you can kind of just copy and paste this this to get the chlorine of what it would be. The CCl4, because instead of an H there, it's really just a chlorine here now, and then bam. And if you count the electrons, we would have the 26 like we had, plus 2 more, so 28, 30, 32. So this is also what would want to be. So now, why is this polar? Why is this one non-polar here, the CCl4, and why is CHCl3 polar? Let's look at the electronegativity. Let's start with carbon and chlorine, actually. So chlorine and carbon, right? We have 3.16 for the electronegativity on chlorine, minus 2.55, okay? 0.61, okay? So there is a, negative slight charge, okay, all out, okay, towards the chlorine, and the carbon is where like the positive charge is, right? But it's all equal because there's all chlorines in each I guess end. So this one would be kind of like a tetrahedral in terms of molecular geometry. Same with the other one as well. Well, point being is that these are all polar bonds. So if I actually were to redraw it, right, it'd be C, kind of like look like this, and this would be Cl, 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 Cl. But because they're all pulling the same direction, okay, it ends up being non-polar because everything, you know, is equally pulling. Now, with that being said though, when you compare this one here, right, still the same shape, okay, alright, still the same shape. The difference is though the hydrogen's electronegativity is a little, well, quite different actually. As I said, these are all polar bonds. So like this is still polar. Oops. This is still polar, polar, polar. Because the cutoff for polar, right, when I did that math, okay, it has to be anything greater than, if I remember correctly, 0.4. And 0.6, although it's not that much greater, it's still greater than 0.4. So it counts as a polar bond. So now let's compare carbon and hydrogen though, okay? Carbon hydrogen 2.55 minus 2.20 for hydrogen electronegativity, 0.35. So this bond right here actually is non-polar, okay? Meaning that now you have a pull, okay? An uneven pull of all these three pulling, but hydrogen's not putting its work in. So because hydrogen is not putting that work in compared to everything else, that makes CHCl3 polar. But with CCl4, because everything is pulling the same amount, because they're all the same, I guess, electronegativity, which does arise from having the same elements in each corner. But you notice that some elements that are close enough in regards to electronegativity, you notice that there's like, although it's kind of polar, it could almost be argued that not really, but you'd barely find out on the periodic table as I'm going through right now. So like, because every element seems to have its own specific type of electronegativity. So exactly, so in situations like that happening, I would say you can err on the side of least likely, because even something like nitrogen and bromine, which are actually quite close, still end up exerting just slightly enough different forces to where it will still be considered polar. So the point being here is that if it's different elements, you're most likely going to be dealing with a polar molecule. Even if it was CH2Cl2 like this, it would still be the same issue, because they would have, because remember it's a tetrahedral, right? So you'd have a hydrogen here, a hydrogen here, a chlorine here, and a chlorine there. Because if we're looking at a 3D structure, you would still have uneven pull on this side, so the hydrogen's not pulling any work in. So even this would still be polar. As soon as you have different elements involved in your like surrounding atom, then you can assume most likely it's going to be polar. So in summary, that's why CHCl3 is polar and CCl4 is non-polar, because of the fact that, you know, as for one, we'd shown it through the whole actual I guess electronegativity, and two, exactly, we're dealing with different elements with the outer shell, outer surrounding atoms, then exactly that would be what you consider polar, because they're different. Okay, so let's see here. We have CHCl3. You can see clear with the Lewis diagram, exactly, the chlorine are quite different from the hydrogen, but more importantly, the electronegativity is different, and it's asymmetric, which results in there being a movement, causing the molecule to behave as a polar molecule. CCl4, you see how it's so nice and evened out and spread out. Exactly. is because it's 4 symmetrical CCl bonds. Now, with that being said though, okay, don't forget that these still count as polar bonds themselves, but because there's polar bonds going the exact way in each direction, overall it becomes non-polar. Now, don't be fooled by the Lewis dot diagram though. If I had, as the last example, CBr2Cl2, something like that, this is still going to be a polar molecule because of the electronegativity. Even though everything looks nice with the electrons all filled out, because bromine and chlorine have different electronegativity, that is why it's going to still be a polar molecule, because they're not pulling the same amount on each side. So with that, this is correct, and I hope with this you'll be able to understand polarity just a little bit better. The trickiest part, honestly, is part differentiating between a polar bond and a polar molecule, because non-polar molecules can still have polar bonds, like CHCl4. So time for a little bit of a water break. So this question is asking us, okay, how do you balance this equation, Mg plus HCl, okay, it turns into MgCl2 plus H2. So for this one, I had to put my guard up because although you're tempted to just solve it just by glancing and filling everything out, for this question specifically, it's actually looking for a redox equation. Why? Because when you assign your electron number to each of these molecules and elements, you will see that magnesium, and for electron numbers, kind of have to memorize how to do it. For elements, okay, it's always 0. So same with the hydrogen over here, okay? And then when you come to molecules, right, halogens are typically -1, and there's only one of them, okay? And that means that hydrogen has to accommodate for that. And hydrogen is typically +1 when bonded to anything. Means that they're typically just as +1. So same thing here, the halogen is -1, and that means there's 2 minuses, so magnesium has to make up for it by being +2. Okay, so magnesium, okay, in a sense, if you wrote down the half equation, it went from the magnesium solid turns into, because remember that plus means it lost electrons, so it'd be Mg2 plus 2 electrons, because that's how much it lost. And the next thing that changed, if you look closely, right, the chlorine stayed the same. The hydrogen went from +1 to 0, and magnesium went from 0 to +2. So we don't write the chlorine down. The next one we actually write is the hydrogen, okay? Hydrogen plus turned into, oops, I wrote that one wrong. It would actually be hydrogen plus an electron turns into hydrogen gas, okay? And because there's 2 of them here, right, H2, you want to make sure that you have the same amount over here. So because you needed 2 hydrogens to turn into hydrogen gas, right, you need 2 electrons, because you need an electron per hydrogen, okay? And with that, actually, conveniently, that actually already balances out the amount of electrons you need, okay? So now we have our balanced redox half reactions, okay? Because in a sense, what you've been able to do here is make sure that the amount of electrons going in are the same as the amount of electrons going out. Hence, there's not really quote-unquote an electron change. So now what we have is 2H plus Mg, it turns to Mg2 plus H2. So now we apply that to our equation here, okay? So we have magnesium, okay, plus, we need 2 H's, and it's attached to the chloride. So it'll be 2HCl, okay, and then that would turn into, okay, MgCl2, as the question said, plus H2 gas. And the reason why we could just ignore the, I guess I could just put, let me just put aqueous. But yeah, so this is what you get as the balanced equation here. What we did there was that we first balanced out the half reactions, which is the electrons, which is exactly what they did here. And then they have the oxidized equation. And then you see here we have Mg2H, Mg2 plus H2, which then you'd put it back into the original equation. So now you know you have 2HCl, which conveniently has the MgCl2, and every constituent should balance. We have 1 magnesium on both sides, 2 hydrogens on both sides, and 2 chlorines on both sides. So this is a balanced out equation. You could just balance it out by just looking at it and saying, oh, we need 2 hydrogens and 2 chlorines. But when you get to more complex redox reactions, you have to balance by the electron change there. Hence why we use the half reactions there. Because there's some questions that where you have to start adding things like the hydrogens, like the protons and water on either side, and you cannot solve that just by a glance. Okay? So this is correct. And now we move on to question 12. What is the Lewis structure of HNO2? Interesting. So Lewis for HNO2. So typically for this, I usually like to put the I guess lone nitrogen in the middle. But let's see if I actually can fill out every requirement here, okay? So let's see. Lewis for HNO2, right? We've covered this, but we're going to keep covering it again and again. Nitrogen, okay, has 5 valence electrons because it's 2s2, 2p3, okay? Hydrogen has 1s1, so it's 1 valence, and oxygen has, start with helium again, 2s2, 2p4, okay? So let's highlight that, and now we have what our electrons should be, and now let's do let's just add it together. So we have 1 hydrogen, 1 nitrogen, which is 5 electrons, and we have 6 times 2, so that'll be 12 plus I guess another 6, so we have 18 electrons in total we have to account for. So with that being said, okay, we have, I will still put the nitrogen in the middle to see how that works, and we fill out its shells, okay? So we have the oxygen bonded, and the hydrogen, okay? And then we try to fill out the outer shells and see how that goes. Okay, and now let's see actually if this is something that actually makes sense for HNO2. Okay, so let's actually write out the electron number. So with that being said, okay, we have the, let's see here, we have, I'm trying to think, yes, nitrogen is 5 valence electrons minus, we have 1 lone pair, so that's 2 electrons, plus 6 in a bond divided by 2, so 2 plus 3, that's equal to 0. Perfect. Oxygen, okay, 6 minus, it has 6, oops, no, not 6, yeah, 2, 4, 6, and then plus 2 over 2, so that'd be minus 1 each one. So in fact, this one doesn't even add up. So what we have to do first is, like, let's check, okay, the amount of electrons it's supposed to be 18, and we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 2 more electrons than we're supposed to have. Okay, so now we have to figure out a way to redraw this. Okay, so because this unfortunately does not work for this one unfortunately does not work for nitrogen, right? So now with that being said, let me just check here. So we have to redraw this in a way that would work. So let's move things around here. Let's see if the oxygen maybe. Actually, let's not put the oxygen in the middle yet. Is there any way we can move the bonds around? Unfortunately, it does not look like we can move the bonds around. So with that being said, let's see here. Let's try putting the oxygen in the middle and see how we can work with that. So we have oxygen attached with a nitrogen, attached with an oxygen. Okay, let's start with that to see what we can do. So NO2 typically, okay, is gonna be like this. Let's see here. NO2, let's start here to make it a little bit easier. So it'll be 6 times 2. Okay, nitrogen dioxide, that's 12 oxygens plus 5. So we want 17 in total, okay? So 2, 4, well actually let's just start with this. So we have 4 right now, okay? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So to move things around, the good news is that these two can move kind of in here to form a double bond. So now we have N double bonded with O, okay, and we still have this here, and the oxygen, unfortunately, awkwardly with 1 right there. Okay, so this right now, this oxygen is incomplete. Okay, but this is the best I could think of right now. I kind of just took the hydrogen out because I guess is the best way to conceptualize this. And if we did the math real quick, we have nitrogen, it's still 5 minus, now there's 2, 1, 2, 3, 4, 5, 6, 7, 8. So that's gonna be 4 minus, whoops, it has 2 lone pairs, so it'll be 2, okay, and then it has 6 in the bond, so 6 over 2, so it's still going to be equal to 2 plus 3 equals 0, so it still works out. The first oxygen, it has 6 minus, it's going to be 4 plus 4 over 4, that's also equal to 0, good, and the second oxygen has 6 minus 4, 5 plus 2 over 2. So this actually works out for now, but this oxygen itself is unstable. So that is actually where the hydrogen comes in finally. So the hydrogen kind of swoops in because remember it's 1 electron, so it goes in like that, and then now we have H O N. So for this one we kind of really had to I guess work through into the different setups, and exactly I think the way I solved this, the best way was to actually ignore the hydrogen for the meantime and just solve NO2 first, and then from there I worked on actually solving where I was able to see where the hydrogen would fit into the rest of the equation. So this is actually what we would have for the Lewis for HNO2, and then we check the math again. So we know that the first oxygen already had that, and actually now the second oxygen has the same thing. Oops, no it doesn't. The second oxygen now has actually, it's still going to be 6 minus, but now it has only, oh, that's why it looks the same, sorry. So it would actually be the same because I was missing the double bond here. So actually yes, it would actually be the same, because now, just like the other oxygen, it has two bonds, meaning that there's 4 bonds, so 4 over 4, and 2 lone pairs, which is at 4 in front. So both of them are now at 0, and the hydrogen, this is the last check, going to be 0 plus 2 over 2, exactly. So that one equals 0 as well. So now the electron numbers all look nice, and this is what the element look like in the Lewis dot diagram. To redraw this with bonds, it will be kind of like this: H, O, N, O, like that. That would be HNO2. So yeah, so they kind of just guess, because exactly, even for me, I have a hard time conceptually how you know how the bond would be like this. But exactly, I think the best way to solve this question would be to ignore the hydrogen at first and try to solve NO2, because then you'll see there that nitrogen is still in the middle, but you wouldn't assume a triple bond like I did here. I mean, 3 bonds in each corner like I did there, because that would be like NH3, you know? So you kind of have an assumption of what it would look like, which is important to try to redo it as if the hydrogen is not there. And exactly, you see, it has like that. So they try to fill in the skeleton like they did, and then they completed the octet, and then they realized that oxygen want to share the bond here for it to have everything have the perfect electron number that's supposed to have. And yeah, so this is HONO. So this is correct. I do wish they kind of delved into more how you figure out if it's HONO, but the point being is that they figured it out. I figured it out at least using NO2 first. So now we move on to question 13. Okay, is KOH an acid or a base? So with this might be a relatively short question. But for this one, we have to really understand what it means to, I guess, be even something that's bonded with potassium. Okay, if you look at, actually not going to look at that yet. When you actually have the formula, right, for KOH, when it reacts with water, okay. In fact, we don't even actually put it reacting with water. So they actually do, when KOH is submerged in water to form an aqueous solution, right, it completely dissociates, as it is just going to be K plus ions and OH ions. Okay, so now that we have, this is what actually dissociates into, that is really what KOH does in water, right? Now we look at this part, okay, because remember the definition of a Bronsted-Lowry base. So potassium, unfortunately, it's really just by itself. It has no valence electrons, so it cannot accept hydrogens, and it has no protons of its own, so it cannot give any hydrogens. Okay, but OH minus, if you drew its Lewis dot diagram, just going to do a shorthand. Look at all the possible, remember it's OH minus, right? So the oxygen not only has a reason to try to make sure it gets more positive, but look at all this lone pairs it has. It has this lone pair to attack hydrogen, this and this to attack the proton, I mean. Okay, so with that being said, okay, it will kind of just go on. You see there's a proton running about, okay, and remember that the OH minus has that because O only gives 6, hydrogen gives 1, so you need an extra to have 8, which is exactly, there's 8 electrons here. So hydrogen comes in, the OH snatches it, forming H2O. Okay, and if you look at the number as well, exactly, so for the first one it was 6 minus 6 plus 2 over 2, so that'd be 6 plus 1, that's 7, so it was -1, hence why it was -1 there. But here now we've been able to get another electron, so that's another hydrogen bond, which is something it really wants. And also it would be 6, well, it's not 6, it would be 4 now, plus 4 over 2. Okay, So that's actually going to equal 0. So it's gotten another hydrogen bond and it's been able to resolve its charge. So something that it really wants to do. Hence why water molecules are such a stable and, you know, something that it really likes to be. Water is everywhere and stuff. Because of this, actually. So if we rewrote the formula, it would be OH plus H2O, because that's usually what we use is the person that's going to give hydrogen, okay? So it's going to be written like this. Sorry, I just want to make sure this arrow is looking nicer. So OH plus H2O turns into H2O. Oops, that's not H2O. It's H2O liquid. H2O liquid plus OH minus. So really it just switched protons. But if we accounted for the base and conjugate acid, we have the base here, and the conjugate acid would be that one, and this would be the acid because it's now giving, the water is giving that OH the base, OH the proton, and this one becomes the conjugate base. So the reason why I drew it like this is because since KOH dissociates to form OH minus hydroxides, and the hydroxides react with water to, you know, form this, meaning that follows in both examples the Bronsted-Lowry definition of a base, and the K is not doing anything other than just being an ion in the solution. In total, this one makes KOH a base because its constituents, aka specifically the hydroxide, is working as the base in this situation. So exactly. With that being said, it is a base, and I wanted to actually show you this because if you actually scrolled down on our table value, right, OH is considered like one of the strongest bases, like the strongest bases you can have. So KOH would be working as a base because as soon as it produces hydroxide, it's gonna make the solution more basic. Now, in regards to knowing whether it's a strong or a weak base, those ones, when formed with hydroxides, it can be a little tricky just because, if I recall, I don't think every metal bonded with hydroxide is as soluble. So depending on its solubility of the actual solid, depending on how it works as a strong or a weak base. So, point being though is that when they say it's a base, that is correct. Okay, so KOH is a base because it separates to form K and OH minus, and it's the OH minus part that makes it base. What is a Lewis structure for POCl3? For POCl3. So for this one, I'm going to actually assume here that the phosphorus is the one I want to be in the middle because it has, I guess, the most valence electrons. And you know, back to what we love doing, we want to find out the valence electron amounts. So let's start with the oxygens. We know we've done it a lot. We start at helium, and it's going to be 2s2, 2p4. That means 6 in total. And also it is on the 16th column, and that makes it easier for you. Chlorine, same thing. It's starts at neon this time instead of helium. And it'll be 3p. Whoops, I almost missed the s. 3s2, 3p5. And now phosphorus is just 2 behind that. So starting at neon again, 3s2, 3p3. Okay. So now we know it has 5, 7, and so I guess the one in the middle wouldn't be the one with the most valence electrons, but the ones that I guess have the most space for bonds, if that makes sense. So I'm gonna put the phosphorus in the middle because that's what I'm assuming right now. And phosphorus likes to break the octet rule. It's one of the rule breakers. There are a few of them on the periodic table, but it's one of them that doesn't really care for the octet rule, and can have more than 4 bonds, as in 4 single bonds surrounding it. But let's first find out how many electrons we need. So we have phosphorus. We know it's 5 now. Whoops, sorry. We have 5 there for phosphorus. Oxygen 6, chlorine 7 times 3. So that's 21 plus 11. That's 32 in total. 32 electrons. Okay. So now with that being said, we have, let's just put phosphorus in the middle for now and kind of work our way there. Hopefully it does balance out, since there's 4 things surrounding it. As I said, we want to just make sure we have that as a beginning. O, Cl, Cl, Cl. Okay. And how many valence electrons does it have left? So chlorine, it wants to have, because only sharing, each one contributes 1, right? So chlorine still has the 6 on the outside. Okay. And now phosphorus, because it has 5, so far it's shared. So far it's shared 4 of the 5, so it has 1 more electron there. Okay, like that. I'm just gonna put it there for now. Oxygen has shared so far 1 of its 6, so we'll have 2, 3, 4, 5, 6. So as you notice, the phosphorus and oxygen still have 1 electron left to be able to kind of share. So those two actually would form another bond here. So these two will move in there to form another bond. Oops. So when you put them, when you redraw this actually, okay, it would be P. As I said, phosphorus doesn't really care about the octet rule, so it's allowed to do that, where now it has 5 bonds, 3 single bond and 1 double bond. And then we redraw the chlorines and the oxygen. And now this is what we assume the Lewis structure is, but we don't know it's right until we actually find out the electron number for each of the elements in there, starting with phosphorus. So phosphorus, okay, likes to have 5 valence electrons, and so right here there's 0, but there's actually 10 electrons in the that are being shared. So divide that by 2, and that does equal 0. The chlorine, okay, is 7 minus 6 in the valence. I mean, in terms of lone pairs, there's 2 pairs of, there's 3 pairs of 2, which is 6, and there's sharing 1, so 2 over 2, so 6 plus 1 is equal to 7. So 7 minus 7 equals 0. And oxygen, 6 minus, okay, 4 plus 4 over 2, because there's 4 electrons being shared, and that also equals 0. So this is actually POCl3. This is the Lewis structure here, okay, as the question requested. And just to conceptualize it, if you had it as bonds, it would be shown as this: a double bond on the oxygen and single bonds on the chlorines surrounding it, with no valence, with no lone pairs on the phosphorus itself. Okay, so let's see how we did. So they wrote a plausible sketch, then they filled it out, and then they realized that they can move. I'm guessing for this one, they realized they can move the oxygen's, one of the bonds, inside to make sure that the electron numbers matched. Okay, so exactly. The p atom is exempt from the octet rule, so exactly that's why it can do that. So with that being said, this is what you have now for the Lewis structure for POCl3. okay? So, with that being said, we've successfully gone through question 14. Let's move on to question 15. What is a compound name for the chemical KBr? Okay, so the first thing we have to do is figure out what it's made of. So K on the periodic table, okay, is potassium, and Br is bromine. Okay, now with this, unfortunately we're not done just quite yet. We have to first figure out what type of bond is it, because they have certain naming rules between like ionic and covalent bonds. So we look at KBr, right, and we see that potassium is a metal and bromine is a nonmetal. So this is an ionic molecule slash compound, okay? Because it's an ionic molecule, you actually drop the INE from bromine, okay? And you have IDE. That is the only change you make, specifically referring to the non-metal part. You just drop it, as long as it's just an element. We're not talking about like sulfates and stuff. When it's just the element itself in the non-metal section, you just drop the INE and turn it into IDE. If you had it for something like K2S, okay, this would be potassium sulfide, because the sulfur, you drop the UR and just replace it with IDE. Okay, so with that being said though, okay, the name for this is indeed potassium bromide. Okay, the point being though, right, is that you drop the little suffix and just replace it with the correct IDE suffix. So you just have to make sure you're kind of dropping off at the right part, because phosphorus is a little bit tricky. It's that one you have to drop it at the after the H, so you have to drop the ORUS, so it'll be potassium phosphide. Okay, but that's how you would go about naming ionic compounds. Okay, and exactly, potassium bromide, or KBr, and that is a compound name of that chemical, and exactly because it's an ionic compound, that's why we name it like that. And it's just some fun facts here as well that they included, that it's been used actually as a veterinary drug, surprisingly. Yeah, huh. So this is correct. That is how you would name it. And let's move on to question 16. What is a formula for iron 3 sulfide? Well, I'm really glad that we just talked about what sulfide meant. Iron 3 sulfide formula. Okay, so with this type of question, you're probably wondering why they said iron like that. Okay, it's because if you look at the periodic table, iron, okay, figuring out its valence electrons can be very tricky. Okay, if you wanted to draw like its electron configuration, it would be you start at argon, okay, and you would have the whole 4s2 and then 3d 1 2 3 4 5 6. Okay, so if you rearrange this, really it'd be 3d6 4s2. Now the reason why it's tricky is because there are actually, you see, as you can see here, it can literally just drop its outer shell, the fourth row, to become Fe2+, and that is known as iron 2 ion. Okay, but the D shell, right, it is actually it has, I guess, half points of stability. It feels more stable when every I guess every orientation in the subshell has one electron only in it. Right now, if you were to draw the not the electron configuration, but the orbital notation, okay, Fe2 plus, okay, you know, starting from argon. In fact, I will start from the actual, so there'll be 4s, there'll be 3d, 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 3d. This is just more so to explain why we have iron 3. So we have 4s2 that's filled up, okay, and we have 3d6. As you notice, we have 1, 2, 3, 4, 5, 6. That's how it works. So you have iron 2 ion, which does exist because it's able to get rid of those. Now, for an even more balanced, or I guess more stable, not I guess arguably, depending on what's comfortable with, why you have these two existing in nature, it will get rid of one of these electrons to where it's now 3d5. So it's really lost now in total, along with the outer shell, 3 electrons. Hence now how we got the Fe3 plus, the iron 3 ion, okay? The reason why I'm saying all this is because you want to know what it means to be iron 3. It means that there's 3 electrons lost. So that's what we have on one side. As a metal, iron 3. Now you notice in the non-metal side, because this is, I want to say, actually an ionic compound, okay? In the non-metal part, we have sulfide. So it's, remember, IDE, ignore that, and you really know that it's sulfur. So it's sulfur. And if you went ahead and, you know, figure out how many valence electrons it has, that would be, you start a neon, okay, and it would be 3s2, 3p4. So there's 2 electrons, I mean not 2, there's 6 electrons in total, meaning if it wants to become like kind of noble gas, it just needs to add 2 more. So typically sulfur, well, sulfide ions would be SU, I mean not SU, why did I put SU? It's just S, sorry. It'd be S2 minus. This is a sulfide ion, okay? Because it would rather gain 2 more to fill the, like a normal gas to be like argon, instead of losing 6 to try to go back to neon. So now we know 3 plus and 2 minus. We want the net charge to be 0. So what's going to happen here to be able to get that is that we want to make sure that we have the lowest, I guess, multiple between 2 and 3, which is 6. So you want to multiply this part by 3 and this part by 2. So now what we have is that we have in total a charge of 6 plus and a charge of 6 minus. You put it together and now you have Fe2 S3, because this way the net charge is 0, and this right here is the iron 3 sulfide formula. Okay, and exactly, they said iron 3, that means Fe3 plus. I kind of just explained why when it comes to the whole orbital notation as to how it can even do that, because of this electron here that it decided that, yeah, I'm just going to drop. So yeah, and then sulfur, we are able to still support that it has -2 charge typically for the ion, and they have to balance it out, and so we get iron 3 sulfide is Fe2S3. So now we move on to question 17. Okay. Is a molecule SF4 polar or non-polar? So for this one, actually, SF4, we're getting a lot of polar, non-polar practice. This is good. Polar or non-polar for question 17. So the first thing I recommend again is to draw that Lewis dot diagram. And since luckily we just did sulfur, you can literally just say it again that it's neon 3 S2 3 P4. That's 6 electrons in total. okay? And now fluorine starts at helium and it's just 2p 2p5, okay? And that means 7 electrons. So for sulfur tetrafluoride, the reason why we say it like that, because as you remember, it's 2 nonmetals bonded together, so this is a covalent compound, right? And for the rules of covalent compounds, you need to include the prefix. So yes, the name actually is sulfur tetrafluoride, not chloride. Fluoride. And it still follows the same rule that the I guess the second part of it has to still follow the IDE. You drop the fluorine INE, the ending, to replace it with a new suffix, the IDE. So 6 electrons here, 7 times 4, so that's 28 plus 6. In total, that is 34 electrons, okay? I'm actually going to use a calculator to make sure. 7 times 4 plus 6, 34, perfect. So for this, I like to still follow the rule of putting the sulfur in the middle, okay? Surrounded by fluorines. Now, remember that sulfur, just like phosphorus actually, is one of the other ones that like to break the octet rule. It doesn't really care about that. So let's put the fluorines out there. So using the same concept though, okay? We have now, it's sharing one of its electrons, so 2, 3, 4, 5, 6, 7. Fluorine is good. 7, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, so of the 6 electrons sulfur has, it's sharing 4 of them, so it still needs 2 more. So you can just put it right there, okay? So let's count. We have 8, 12, 8, 16, 24, 32, and then plus those 2 red ones right there, 34. Perfect. And if we did the actual electron number, we have 6 minus, we have 2 valence, and then it's 6 being shared over 2. Oops, I think I might have done the math wrong. It's not 6 being shared, it's 8 being shared, sorry. Because it's 8 electrons being shared in total. So 2 plus 4, that's equal to 6, so it does equal 0. Same thing with the fluorine. 7 minus, it has 6 in the lone pairs, so 3 lone pairs of 2, so that's 6 in total. And then plus 2 over 2, that is 7, and then that also equals 0, so that's good. This is actually what sulfur tetrafluoride would be. Now to answer if it's polar or non-polar, this is your answer right there, okay? Not only does it have a lone pair on the sulfur, it's not counterbalanced by another lone pair. So if we were to actually draw it, it would look something like this. And so first of all, the bond number, actually, yes, that's the number, that's what I was looking for. The bond number would be 4 bonds, okay, that's what it has with sulfur, plus that 1 lone pair. So the bond number for sulfur is 5, okay? That means, okay, well, not even there yet, but it has 4 bonds and 1 lone pair. So I'll actually show you the official geometry, but this is what the drawing would typically look like when you actually draw sulfur, okay? The electron will be kind of a jerk doing that, and then we have the other 2 kind of sticking like that, okay? So with this, these angles here from the top to the bottom, like pictures kind of like this, it's kind of like a circle with a line through it, okay? That's what it looks like, as in this is where the electron would be, this is where the first bond would be, and this is where the second bond would be. Let me draw a different color. So it's like into the 3D molecule. If you're looking at it from like the side, okay, this is where the first fluorine would be, second fluorine, third fluorine, fourth fluorine up here, and then the valence shell. So when you draw like this though, you can kind of see it, but exactly the point being, right, is that these bonds here between the fluorines, because the electron, the lone pair has so much push, these bonds are just slightly, well not slight, but just less than 120 degrees in terms of that I guess pi. It's not a perfect split pi, and because this thing is also pushing these fluorines to the top, these angles here, they're not actually 90 degrees, sorry, they're actually going to be just less than 90 degrees, because it's kind of just pushing everything to where everything kind of, so it used to be straight, right, but the electrons, the lone pairs are pushing to where it kind of bends like that, and then these ones that are here like this kind of bend like that as in they get close together. So that's the shape we have there. I don't know the actual shape name, but point being is that because now we've drawn it like that, you can see clearly that this double bond here, I mean not double bond, lone pair, has such a electronegative force, because that's like the strongest you can get. It's the electron itself, to where it kind of just pulls everything that way. Okay, that wins a tug of war. So that's what's happening there. Because there's a lone pair there, everything is thrown off balance, making this molecule, the answer is that it's going to be polar. Okay, so let's look at that with the actual Vesper theory. As I mentioned, it was bond of group of 5, and we scroll down to 5 here, 4 bonding groups and 1 lone pair. So it's known as trigonal bipyramidal, and it's known as seesaw. So with that being said, exactly this is what it'll look like. As I said, it's going to be a little bit less than 120, because I think this is a better picture. You see here the bottom parts, they're actually a little bit less than 120 degrees apart, because how strong the electron is. And then the 90 degrees here, it's actually a little bit less than 90 degrees, because that's how strong exactly the electron lone pair is. So in total, it is going to be polar though. And just like that, perfect. It even shows nicely the I guess the bond lengths. So exactly, it's from F to F, exactly. It just shows the total thing. So 173.1 degrees. I mean, if you were to split it in half, you know that each part, when it goes from F to like the middle, is less than 90 degrees. Okay, and this one as well, showing that the circle part is 101.6, which is indeed also less than 120 degrees. So it does say sulfur tetrafluoride is a polar molecule. So this is correct. So let's move on to question 18. Oops. So hexane has a density. Actually, I'm just going to write it all out. So hexane density of 0.766 grams per centimeter cubed per fluorohexane. So it's kind of like hexane, but without, instead of carbons, they have some fluorines instead, and that which makes it polar, because hexane would be a non-polar molecule. For fluorohexane, would most likely be polar. But yes, 1.669 grams per centimeter cubed. And water are immiscible liquids. Okay, so it doesn't give away the density of water, but we do know, I guess from literature, that water density, okay, is, let me actually just write in a different color because it's not given, but it's something we should know. It's something kind of to memorize, unfortunately. It's kind of like 1, typically in the standard temperature and pressure, it's 1 gram per centimeter cubed. That is the density of water. Okay, maybe our physics classes will have that. I doubt it though. Let's see. Oh, yep, density of water, nice. This is a different sheet though, but 1.00 grams per mole in standard temperature and pressure. So let's see the other pieces here that they say. They don't dissolve in one another, so they will form layers. And you place 10 ml of each in a graduated cylinder, along with pieces of high density polyethylene. Okay, so this is a solid, okay? HDPE, density 0.97 grams per centimeter cubed. Okay, that's a piece of it, right? Not just another liquid. Polyvinyl chloride, okay, chloride, okay, PVC, and this is 1.36 grams per centimeter cubed, okay, and Teflon, 2.3 grams per centimeter cubed. None of these common plastic dissolves in these liquids, which is good. Describe what you expect to see. So, the rules of density, okay, are that the heaviest will sink, the lightest will float up top of it, okay? So what we're going to do is just first label it. We want to label, we're going to use, I guess, different colors to try to make it look as different as possible. So we're going to do like a shift. I'll explain what I mean by that. The lightest one here in terms of density will be the hexane, okay? Density of 0.76. So we're going to label this as green hexane, okay? And now perfluorohexane, it's going to be labeled as red P. I might just have to use different colors actually, just for this one. Yeah, perfluorohexane, that'll be P. Yeah, okay. C6F14, as they've given this nicely. Whoops, that wouldn't be it. Actually, it wouldn't matter. I don't mind that actually. Okay, and then water is going to be 1. So knowing this, actually, let's start with that. It's 10 mils of each, right? So because the perfluorohexane, as you see, is the densest, it'll be at the bottom. So if we had a graduated cylinder, right? Okay, that's what it says. Yep, in the graduated cylinder we have 10 here, 20 here, and 30 here, right? The first one would be, let me just make this actually black so there's no confusion. The first one at the 10 mark, okay, would be that C6F14 of perfluorohexane. That'd be the thing that's all the way at the bottom, okay? Water will be the next one because that one is 1.0 grams, which is greater than 0.766 grams per centimeter cubed, okay? Then the last one would be the hexane, okay? So now we kind of have to pick some really bold colors here because now we want to show where each of the plastics would be. So let's pick purple for HDPE, okay? Density is 0.97. So it is greater than the hexane density, meaning it will sink right through, but less than the water, meaning that this thing would be a solid right there on top. So this is HDPE right there, solid on top of that, just like that, okay? And now, with that being said, okay, the polyvinyl chloride, okay, is greater than water, but less than the perfluorohexane. So we can choose this color, for example. This would be now PVC. Oh, that's like what they use in pipes. Oh, that's not a good color. Let's use a different color. Let's use something that stands out from blue, orange. That's a good one. I hope I'm correct. So That's better. So it's going to be sitting right on top of the red, okay? And now Teflon, let's actually just go back to black to make it a little bit easier for us, okay? Teflon. And you notice it's 2.3 grams per centimeter cubed. So that thing will just sink right to the bottom. It's denser than any of the liquids. So this is where the Teflon will be, okay? And just like that, you can actually now see we have a full picture here of what you would expect to see when you put these 3 liquids together along with those 3 plastics, okay? Let's see how we did. Hopefully they have an image. Nice. Nice. So exactly, A, HDPE. Whoops. Yeah, HDPE is hexane layer. Yep, that's what we have. And then next, the PVC is floating in the water, exactly like right on top of the perfluorohexane, and Teflon's at the bottom of the graduated cylinder. Okay, and Teflon is dense, so it will sink further than the perfluorohexane. So we have it correct. We have hexane, water, perfluorohexane, HDPE, polyvinyl chloride, and then we have the Teflon. Okay, this is correct. That was quite enjoyable. I like drawing that picture, and it really shows exactly like how densities work, and also kind of emphasizes how chemistry and physics are not too far apart when it comes to figuring things out. So this question is asking, okay, what is the hybridization in carbon dioxide? So first we have to figure out what carbon dioxide would bond as. So once again, Lewis dot diagram, and you know what that means, electron configuration, just to make sure we know how many electrons are out there. You can still definitely use your periodic table to see it right away, but you know, just a good way to just keep practicing this writing down. So for carbon it's helium, okay, and it'd be 2s2 2p2. Oxygen, started helium as well, 2s2 2p4, and we see here that carbon will have 4 in its valence, oxygen will have 6 times 2, that would be 12. So we have C. So in total we have 16 electrons we're working with. And as we said, carbon has 2 more, and oxygen has 1, 2, 3. The one that's left, because it's sharing 1, right? So it has 5 more. 4, 5, 4, 5. So these 2 will go in here, and these 2 will go in here. Okay, so in total what we get is C. Oops, we can't show that yet. O, and this is actually what would also count as a, even though it has polar bonds, still a non-polar molecule, because of the fact that now carbon, no lone pairs, and the oxygens are pulling equally at each other. So in summary, it would actually look linear, and that would be carbon. Okay, so now the hybridization, the way it works, right, is that in simple terms, really, there is a lot more complex that comes with it, but in simple terms, when it has more than one bond, it starts hitting that p orbital kind of thing. So it starts as S, and then you add on to it. So S is like the 1, and then you see carbon has 2 double bonds, but these double bonds still count as 1 bond. Okay, even though it's a double bond, it still counts as 1 bond. So 2 double bonds, meaning there's now S, okay, and then P. That would be hybridization for carbon. Okay, now for the oxygen though, okay, this is where it gets even trickier, right? Lone pairs also count as a quote-unquote bond, okay, or at least a hybridization energy. So oxygen has 1, so start the S, and then it has that P, as in like 1 lone pair, but it has also another lone pair, so it'd be sp2. This would be the hybridization for oxygen. Okay, so hybridization is CO2, for the oxygen is sp2, for the carbon is sp. And exactly, carbon has sp, oxygens have sp2, which we found because of the Lewis dot diagram. Okay, and it says the sum of the numbers of atoms bonded to the central atom and the number of lone pairs is the steric number, which is what this is accounting for. So exactly, so that's why we have sp, sp, S, that's what it starts with, and sp would be 2 bonds, sp2 3 bonds, sp3 4 bonds, and then when you start approaching sp3 like D and stuff, those are the ones that start breaking like the octet rule and everything. So they have the Lewis structure, perfect. So the carbon only has 2 bond groups, so it's sp as I said, and oxygen has 3, 1 bond group and 2 lone pairs, which makes it sp2. Okay, this is correct. 19 questions in. There's one question 20. What is the electron configuration of silicon? Well, I'm glad you asked. I'm sure if you're getting so much practice, you might be getting sick of these. Electron configuration of silicon. Okay. So remember, we can do a shorthand and longhand version. For this, I'm just going to do a shorthand version because we've been doing so much that we kind of now understand how it navigates. So we start at the most recent noble gas, and then we count from there. So silicon, okay, is on the 3rd row. So 3s2, and then 1 2. So it'll be 3p2. So just like carbon, silicon will most likely have 4 valence electrons, but this right here is a short-handed electron configuration for silicon. Okay. Yep. Neon 3s2 3p2. So yeah, this is correct. By the end of this, I hope that you all will be experts when it comes to doing the electron configuration. So now number 21. Let me take a quick water break here because we're 2/3 of the way through. Can't believe I actually woke up at 7 a.m. on a Saturday. More electron configuration using both the SPDF notation and the orbital box diagrams. What is the relationship of the atom's electron configuration to its position in the periodic table? This is a great conceptual question. So, electron configuration for Mg and argon, I think, both SPDF notation and orbital box. Okay, that was the orbital notation when I showed the electrons from that other question, and now they also want to know the relationship between periodic table and electron configuration. So let's start by looking at the periodic table here, and now we're going to do the electron configuration for magnesium and argon. So good news is that we're going to do shorthand for both. So magnesium, right, you start from neon, the previous noble gas, and then you see here it's 3s2. If we were to redraw that, let me just make a different color because this is where we start answering. Okay, we have just one orbital box with 2 electrons in it, and it would be the 3s orbital. That would be magnesium. Now we want to do argon, which is actually a noble gas. So you don't start with the noble gas argon, you still start with the prior noble gas, and you put 3s2, and then it's 3p6 because you counted from aluminum to argon. Okay, and now for the orbital notation, we have neon still, and we have now 4 because each orbital can only take 2 electrons. So it'd be the 3s, 3p, 3p, 3p. 1, 2. Okay, and now this would be argon. Now they're asking you what the relationship is between the periodic table and the electron configuration. Great question. Okay, so if it's still in the S subshell, you will see, just as the other questions we've been doing, okay, if it's still in the S subshell, it's going to be on the first or second column. Okay, when you have it ending in the P subshell, that is between the 13th and the 18th column. Only exception is helium. Helium still counts as an S. Okay, but everything else starting from boron all the way to radon, those ones are going to be in the 13th to 18th column because that is the p orbital. D orbitals are a little bit trickier, okay, in terms of noting where it is on the periodic table, because you have to make sure is that, I guess the trick is that you have to make sure that there's no, you will definitely see, like in terms of at least like a 4s2 starting from there, or even a 5s2, but when you have an s orbital and no p orbital, that, and okay, no s orbital, no p orbital, but a d orbital, okay, that means that it's actually going to be in your transition metals section, column 3 to column 12. So if I had like 5s2 4d4, right, as an example, okay, and for it to start at 5, you know this has to be the 4th element there, so it'll be Krypton. If I said this, right, obviously this is the wrong way because you want the 4 to be there and the 5 to be there. So if we rewrote it, 4d4 5s2, what element am I talking about? It's going to be 1, 2, okay, that's the 5s2 part, and then the 4d4 would be 1, 2, 3, 4. It'd be molybdenum, okay? Technically, actually, this one might actually be 4d5 5s1, but that's later on when you try to learn about specific things that they like to do to keep their energy levels good. But point being is that you have a D shell and an S shell, but no P shell. That is how you know that for this electron configuration, it's going to be in the transition metals section. And same thing as well is that if you had no P orbital, like subshell, but you had S, D, and F, it's going to be in your lanthanum and actinium series, okay? So that is a relationship between periodic table and electron configuration. Depending on the constituents of the electron configuration, that tells you where it's going to be on the periodic table. So as a quick review, columns 1 and 2, only S. Columns 13 through 18, it has S and P. Columns 3 to 12, it has sorry, I'm blanking out. It has only S and D, okay? Lanthanum and actinium series has S, D, and F. So the trick here is that for these, the D and the F, okay, the transition metal lanthanum actinide series, they don't have the p orbital, like the, I guess, most outer p orbital. And for the elements like in the columns 13 to 18, they can have everything else, but the important thing is that they will end in that p orbital. That's the important part. So they could have S, P, D, and F, but the key thing is that the p subshell is still there. Okay, so let's see how we did here. So we did a shorthanded version, so all we needed was this last 3s part. Okay, and for this, I usually don't put the X, Y, Z, because like although those are coordinates, I just kind of make sure that it's known that they're all p orbitals. And then for the argon, exactly almost the same thing, but it has the 3s and then the 3p6 part, exactly, which is what they have here: 3s2, 3p6, and that's it. So exactly, it has, oh, I didn't even explain that part. The number, okay, the coefficient in front tells you what row it's going to be in. That's the last information you needed. So when I said 5s1, even for that example, right, you know that at least you start on the 5th row, because remember that D shells, they're -1 of the what's it called, the shell number. Okay, so exactly it was in the 5th row for that example. Because magnesium and argon are both on the 3rd row, that explains why we have it 3s2. So exactly, so that is all the information I have related to this periodic table. Yep, and it's, as I said, the valence shell, because that's all we looked at here actually. That's why I like to keep the shorthand version, because really the new information after the noble gas tells you where it is on the periodic table. Hence why they mean by valence electrons. Okay. What is the lowest structure for NH3? Ooh, I think I briefly touched on this when we're trying to do the HNO2, where if it was NH3, we kind of just put nitrogen in the middle, which is actually what we're going to do here. So Lewis for NH3. So for this one, we're just going to keep practicing. Start at helium for nitrogen, and it's 2s2 2p3. That's 5 valence electrons, and remember it's on the 2nd row. And hydrogen, it's just by itself, 1s1, first element, 1st row, 1 electron. So that's 5 plus 3, so it's going to be 8 in total. So we have nitrogen with those 3 bonds. That's hydrogen, 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 and then so far of the 5 electrons nitrogen has is only shared 3, so 2 more, and that might be it for NH3. Let's check the math. So we have 5 minus 2 plus 6/2. That doesn't indeed equal 0. And this one is 1 minus 0 plus 2/2. So this is it for the lowest structure for ammonia, which that is what this is, since that's one thing you have to memorize. So yep, ammonia and H3, and that's it. Yeah, I just like drawing the Lewis-Dot diagrams as even the bonds as dots, because that just really emphasizes and makes it easy to count the electrons there. So yeah, quite a short question, but exactly, just more so to understand the Lewis-Dot diagram. A lot easier to approach than the HNO2, because for that one we didn't have to rearrange anything. So for this one, actually, the Lewis structure for OCN. So this is going to be a little bit trickier, because just like the other one, we might have to do some rearranging. So let's actually start with Cn, but let me just write down the question. OCN minus. So once again, starting at, look at the periodic table, it's all going to be nicely on after the helium. So oxygen is 2s2 2p4, carbon is 2s2 2p2, nitrogen is 2s2 2p3, really close to each other, but 5 here, 4 on the carbon, and 6 on the oxygen. So in total we have 6 plus 4 plus 5, and then because there's a minus here, it's going to be plus 1 more electron. So that's 6 plus 4 plus 6, that's 16 in total electrons. Okay, so just start with the cyanide, right? That's what Cn minus is. Okay, so that one typically is just a 4 plus 5, and then plus that minus, right, plus that electron, it's going to be 10. So we have C and N. Okay, and so it still needs 1, 2, 3, and nitrogen is 1, 2, 3. Okay, whoops, sorry, it's only showing 1, so 1, 2, 3, 4. Okay, so with that being said, it looks quite unstable right now, but remember there's just one more electron thrown in there. So if we did this and that, and then these ones went in as well, and then you'll be able to actually see the picture now of where it's carbon, N, and because we have that one electron I haven't accounted for just yet, it's going to be right there. So let's see first if we have this correct. We have nitrogen, which is going to be 5 minus 2 plus 6 over 2, 0 indeed. And carbon is 4 minus, it has a 2 plus 6 over 2. So it's going to be minus 1, which makes sense because exactly there's an extra negative, as in there's an extra electron. So that is what cyanide looks like, okay? Now, how would we throw in an oxygen? Okay. It may be possible, because right now this has 10. If we threw in the oxygen attached to the carbon, right? Okay. All right. And now it's sharing 1, so carbon still needs that 1 extra one to be that 5, because right now it's sharing 3 with nitrogen, 1 with oxygen, and 1 more, because that's what it was in the, because 2 plus, did I put, yeah, 2 plus 3, that's 5. That's how it has 5 there. And the oxygen is sharing 1 right now, but it still has 5 more to account for. So 1, 2, 3, 4, 5, 6. So what's going to happen is that this actually will go in here, this will go in there, and now, ooh, would it? It would not, because that would actually break the octet rule. So in order to just not try to upset the octet rule and move the actual electron to just a more stable environment, because oxygen wouldn't mind actually having that negative. So this carbon is going to go, I guess it's easier just to draw it at the bottom. This is going to actually just move over to the oxygen, okay? Because if you count it before it moved anything, we actually still have 16, because it's 2, 4, 6, 8, 10, 12, 14, 15, 16. So it's like that would move there, and now we have C, okay, nitrogen, and then because now, whoops, I forgot the actual bond, bonded to the oxygen, okay, now the oxygen gonna have this. So this right now should be the OCN. Now let's actually do the math real quick. Nitrogen stayed the same, so we don't have to do that again. Okay, carbon now is gonna be 4 minus, is now sharing 8, okay, over 2, so it's gonna equal 0. Perfect. But where's that -1 charge? Let's look at the oxygen. 6 minus 6 plus 2 over 2, because only sharing 2 electrons. That would be 7, so it'll be -1. And that's where that negative is on the oxygen. Okay, that's where the negative is, and exactly that's why this whole thing is negative. Okay, so that is the Lewis structure for OCN. Let's see how we did. Determine the central atom. Typically it's carbon, because it can create the most bonds. They have a lot of rules here. You see how we kind of troubleshoot it though? That's also a way to approach it, because sometimes the rules, if you try to be formulaic, you can end up getting stuck and not know how to change it around. Based on the last question we did, where it was HNO2, I realized that maybe sometimes it's good to start step by step, because exactly we were able to get cyanide, which that is CN, and then we were able to now see how adding an oxygen would change cyanide, because we see that it wouldn't really make much sense to go on the nitrogen part, because nitrogen is already stable and balanced, but the carbon is where the -1 was. So yep, that is exactly what we have. I got scared for a second because I don't have it in terms of bonds. I have it in Lewis dots, but exactly 3 pairs, which is a triple bond. Exactly, and then we have just 1 bond sticking out the carbon, and exactly the negative is on the oxygen. So yeah, and yeah, so that is going to be the structure for, let me see here, exactly, just looking at the rest of them. This nitrogen here, exactly, it doesn't really explain why it doesn't work, but it doesn't work even though it is overall, the oxygen is 0, carbon is 0, and they're just 1 minus 1. The reason why that doesn't work is because we already actually were able to solve that issue when we did cyanide. Nitrogen was nice and comfortable, so making it now, I guess, regressing back to it wouldn't make sense, because we established that there is a triple bond between the carbon and the nitrogen. So yeah, now as well as question 24. So, how do you calculate the pH of hydrochloric acid? So this will officially be, or 80% done, but oh yeah, I recognize this. I almost blanked out for a second. pH of hydrochloric acid, HCl. So I believe if you saw my last session, I did explain this, but I'll explain it again. To find out how to calculate pH, you have to first understand whether you're dealing with a strong or a weak acid. And how do we know if it's strong or weak? We need to know the Ka, the dissociation constant for that acid, okay? And if it's greater than 1, that's a strong acid. And if it's less than 1, but it would never be less than 0, because there's no, it needs to dissociate. You can never put something in and it forms more of that thing and there's nothing in the solution present of it initially. So this would be the weak acid border, okay? So now knowing that, let's move over to our acids or bases sheet. Hydrochloric acid is sitting all the way over here. It doesn't even bother saying what the Ka value is. It just says that because it keeps increasing here, right? And if 1 is here, that means everything above hydronium ions, H3O, is going to be greater than 1. So with that being said, okay, hydrochloric acid is a strong acid. Now you're probably wondering, so Fejiro, why does that matter when it comes to figuring out the pH? It matters because when you write the formula down, right, it dissociates completely. Plus H2O. Okay, there's no backwards arrow. This is just going to form Cl minus plus H3O plus. Okay, and because it dissociates completely, there's going to be a 1-to-1 ratio. For every 1 mole of HCl, there's 1 mole of Cl minus, and more importantly, 1 mole of H3O plus. What does that mean? Because the formula to find out the pH is negative log of the concentration, so moles per liter. So exactly, this can actually even be substituted with, like, for every 1 molarity of it, moles per liter, it'd be the 1 molarity as well for each one. And exactly, it's a negative log of H3O plus concentration, which is, as we've established, is just a 1-to-1 relationship. So what does that mean? It means that if we had 0.34 moles per liter of hydrochloric acid, we would also have 0.34 moles of H3O. Okay, meaning that you can literally just plug in this number into that equation over there, negative log of 0.34, okay, and you get a pH, okay, of 0.47, just to be able to round. Okay, and you see that is actually a very low pH, which is fitting for this strong acid. It's just 1-to-1 ratio. All the parts of it dissociated, hence how we got this pH right here. Okay, so yeah, let's see how we did. Exactly, we had that important formula, which is what we need. pH equals negative log H3O. We have the right equation of how it dissociates, and for this one they used 0.20, and exactly just plugged it in, and it will form that answer they got. If I plugged in 0.20, I get 0.698, which just rounds up to 0.70. That is the way you calculate the pH of a strong acid like hydrochloric acid. If the question was asking for how to calculate a pH of a weak acid, that is a whole different process with many more different steps. So 25, nice. What is a molar mass of benzene? So the hardest part of this question, unfortunately, which is what the already answer is given, is knowing what benzene is. Benzene refers to the carbon ring, okay, that's, has resonance structure in it, and it has the hydrogens out there like that. Okay. All right. And typically just drawn like this because you don't need to show the hydrogens, but only, just as this for your information, right, only one hydrogen can fit in every corner because it's a combination of single and double bonds all around the benzene, all around the ring. So with that being said, in total, benzene is the molar formula, molecular formula is C6H6, okay? Sorry, just C6H6. So now they're asking for the molar mass of benzene, okay? So with this, kind of like what we did before, we have the constituents, 6 carbon, 6 hydrogen, okay, times 12.011 times 1.008, okay, 12.0. And I know this because I've done carbon quite a bit times, so I'm getting used to those numbers. 12.011, okay, times 6. So that's 72.066. And then 6 times that is 6.0. 8 times 6 is 48. And then we add those two. So the molar mass of benzene is 78.114 grams per mole. So that is a molar mass of benzene, okay? So relatively straightforward. Just make sure that you recognize what benzene is. That's the hardest part of this question. And so we got it. Our answer is slightly different just because, you know, he has a periodic table he's referencing and I have my own. But other than that though, this is correct because these numbers are fairly close to each other, meaning that they have the correct amount of hydrogens and carbons. So now 26. What is a balanced overall reaction from the half reactions shown above? So this is what counts as a redox reaction. Okay, we have Cu. So let's write a question. What is balanced overall reaction? Okay, so we have Cu to Cu2 plus, and we have Au plus to Au. So the way you balance these out is by electrons, and you're probably thinking, but I don't see any electrons. That's why we have to add them. So with this, copper went from copper to copper 2 plus, meaning that it lost 2 electrons, hence why we put plus 2e, because now it's separated from the copper. Silver, on the other hand, okay, goes from silver plus to silver, meaning that actually this gained an electron. So now we can see, based on the copper and silver, how many electrons each lost and gained. But we want the net electron change to be 0, okay? So then to make sure these two cancel out properly, we need to now double everything on the silver, or is that gold? That's gold, sorry. On the gold side, allowing the electrons to cancel out. So our full formula, when you write the reactants plus the products, it'll be 2Au plus Cu. This will be aqueous because that's an ion. This is probably going to be a solid. And it's going to redox reaction into Cu. We'll actually write it down the same way. 2Au plus Cu2 plus. Okay, so 2, 1, 2, 1. That's going to be your equation there. Okay, and what this is pretty much saying in this redox reaction is that when you set up your I guess your not battery, but your redox, your cathode, anode, that setup, I'm forgetting the word for the actual thing. It's kind of frustrating, but point being is that you'll have some some gold in the solution and copper solid bar, right? And that copper is going to be being dissolved while you're going to be actually forming more gold on the I believe it's going to be the cathode part. Don't quote me on that, but that's the concept of like redox in terms of how electrons are moving from one place to the other. But yeah, so we have the oxidation half reaction and reduction half reaction. So that's what I mean by redox. Redox stands for reduction oxidation, and the way, as you probably see from these pictures, that oxidation means loss, so oil rig if you remember. Reduction is gain, okay? Oxidation is loss of electrons, that's why it's oil, and rig, reduction is gain of electrons. So copper was oxidized, gold was reduced, and that is exactly what it has here. And then you had to double it to make up for the copper. And then now when we put it together, the overall equation, copper plus 2 gold is equal to copper 2 plus 2 gold solid. So this is correct. So yeah, So I did just balance it without really discussing the concepts, but yes, this is going to be your best friend, okay, to understand redox. Oxidation is loss of electrons, reduction is gain of electrons. Almost counterintuitive, but that's just how redox reactions work. The density of the ethyl alcohol is 0.789 grams per milliliter. What is a volume of 35.5 grams for ethyl alcohol? So they're nice enough actually to give us a formula to calculate density. What if we didn't have that? How would you go approach this question? Same way you actually try to cancel your units. So you started out with, well, actually let me write the question down. Density of ethyl alcohol is 0.789 grams per mole. What is a volume of 35.5 grams of ethyl alcohol? Okay, so let's start with what we know. We know we have 35.5 grams of ethyl alcohol. So if we want to get rid of the grams, we want to make sure we put the grams now in the denominator, which is 0.789, and then equals 1 mil. So to find the volume actually is going to be 35.5 divided by 0.789. Okay, that is going to be 44.99. If we want to round it to the nearest significant digit, because there's 3 signigs, it's going to be 45.0 mils of ethyl alcohol. That's how you solve it. So you need to know the formula actually. But for context actually, as you see there in grams per, milliliters, right? The way it works for density, right? To find density, that weird P, okay, is going to be mass over volume. This is the density formula. So you can rearrange it however you want to find mass or volume. In this case, they're acting for volume. So volume is equal to mass over density. But I didn't need to know that formula per se because I was able to look at the units and make sure that I was canceling the right units. Okay? So just another trick. That way, like, you don't feel like you're being overwhelmed by all these equations you have to memorize. But yeah, that's what they did here. They rearranged it, and exactly they got 45 mils. So this is correct. So now let's move on to question 28. Now, is the ammonium ion an acid or a base? An acid or a base. So ammonium, exactly as they wrote there, NH4 plus. So for those that may just be tuning in, you may not know the answer, but for those that hopefully saw me do the question of whether ammonia was an acid or a base, you should be able to answer this one. But for this one, we're going to approach it the same way. Our best friend, electron configuration, to say how many valence electrons. Nitrogen is helium, 2s2, 2p3, so that's 5 electrons. Hydrogen is just 1s1, that's 1 electron, so 5 plus 4 in total here, but minus 1, so it's actually going to be 8 electrons in total because of the fact that there's a plus, meaning that we lost an electron. So nitrogen is going to be having the double bond, that's in the left place. Okay. And that is going to be what this NH4 is going to be. And then we also figure out, because nitrogen typically is sharing 4 of the 5, but it wouldn't have its 5th one because of that plus. So this is NH plus, and the positive is actually going to be probably in here, because if you did the math really quickly, you would see that nitrogen prefers 5 minus 0 lone pairs, and H shared So it's going to be 1. So that's where our positive is right there. So it's asking if ammonium is an acid or a base. So it can actually get rid of that positive by just getting rid of a hydrogen. Okay, as I mentioned, although it loves its hydrogen bonds, it also loves being electronically stable, as in like as close to 0 as possible. So if it gave away one hydrogen or one proton specifically, so it selfishly kept the electrons, but the hydrogen he just kicked out the hydrogen, right? That makes it a proton donor. So it's donating this H plus out, right? And if we rewrote it, for those that were here earlier, you would notice that we actually just get NH3. And if we did the math here for the nitrogen, you'll see it's 5 minus 2 plus 6 over 2, 0. So it actually now was able to meet its requirements. Although it did lose a very favorable hydrogen bond, which it likes, it actually now is a balanced, as in it's now the electron number is now 0. So it's like, you know what, I guess it was worth it. But the key here is being that it was able to give up a hydrogen, a proton donor. So by Bronsted-Lowry definitions, it is going to serve as a Bronsted-Lowry acid because it's able to give away a hydrogen. Specifically in this case, you know, it has 1 to spare. As I mentioned with the ammonia question, it wouldn't keep giving away its hydrogens because it doesn't get any favor. It doesn't get any favors from it. It's not only become away from 0, as now it's going to be -1 and stuff, but it loses another hydrogen bond, which it doesn't want to do. So with that being said, if you wrote the full formula, right, it'd be NH4, okay, plus water. I don't like putting H3R. I get too excited, I guess. And it's going to turn into NH3, okay, plus H3O plus. So with that, in this case, right, because it's losing an electron here, you can actually see that it's going to be its conjugate base. It's going to be the acid, and the water gains, losing a proton, and the water gains a proton, so it goes from B to its conjugate acid, because the water is taking the proton from the ammonium ion. So with all this being said, we have now 2 supports. Here in this Lewis dot diagram, we can show the hydrogen leaving to form a slightly more stable NH3, because now its electron number for the nitrogen is 0. And here we actually show it with the formula as well. So this makes ammonium ion, okay, is going to be an acid. Okay, so that is the answer to that question, and let's see how they did. Bronsted-Lowry acid donates, base accepts. So we got that part right. They have this formula showing like the opposite, but realistically speaking, you can write it like this as well, because it's saying the same thing. And you can see here the hydroxide takes away the proton to form water. But in all concepts still, ammonium is donating a proton, which makes it an acid. So yeah, and now let's move on to question 29. What is the structure of HCO3 minus? Okay. Sometimes I think I'm scrolling down on this side, so then I kind of already start scrolling down the answer by accident. But structure of HCO3 minus. So for this one, like I said, I think it'd be better to just leave out the hydrogen to begin with, just in case. Okay. So what does that mean? It means we're going to try to solve, I guess, CO3 2 minus then, because hydrogen always adds an extra electron. Whoops. Yeah. CO3. No, it would still be CO3 minus, because all you're doing is kind of like that. Trying to think about this. Yeah. We actually just, in fact, you know what I said? Let's actually first find out from the periodic table, the values for it in terms of the electron configuration. For carbon, start with helium again, 2s2, 2p2. Oxygen is start again with helium, 2s2, 2p4. Okay, so now we know, and you know, hydrogen is just 1s1. That comes in later, but point being, we want to calculate for everything. So that's 1 plus 4 plus 6 times 3, that's 18, and then plus 1 more. Okay, so that's 18 plus 18 plus 4 plus 1, not the hydrogen, but that extra 1 there. So we have 23, well, we technically have 24 electrons in total. We're going to solve it like the hydrogen's not there. So we're looking at CO3 minus. So we want to at least account for 23 of that 24. So CO3. I'm just going to put carbon in the middle like this as a start. Okay? Because it's sharing 1 each with the oxygen. At least this is the theory so far. Okay? And now we're going to see how many valence electrons are left. So oxygen here is sharing 1 of its 6. So 2, 3, 4, 5, 6. Same with this one. 2, 3, 4, 5. And then, yep, 6. 2, 3, 4, 5, 6. And now carbon, of its 4 electrons, it's sharing 3 of them, so it needs 1 more. And there's that extra one as well. That one, I think, to make it make sense, because we want to form at least 1 double bond, because all carbon can handle. So we're going to form a double bond here. Okay. And that's going to be C, a double bond here. And now we still have, this is where it gets tricky, right? Because right now we have only 22, I believe. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, 20, 21, 22 electrons. Yes. So put those over there. That will make a double bond there. And then we still have this. If we filled out 1, because that's negative, right? We actually now have space for the hydrogen. It would actually go here. Okay? But point being, though, is that we would have, if we redrew it, C, give it a little more space, C, O, another oxygen here, another oxygen here. Okay? Double bond, 2 more. And then this was gonna have that one like this, and this one is gonna be like that. Okay, so with that being said, this is what we have so far. So now we have space for the hydrogen, okay, because this one's still that 1 extra electron that was left after we added the other the 23rd one. So this is where the hydrogen comes in, like that. So this actually is a structure for HCO3 minus. And if we did the actual math for in terms of like the electron number, carbon exactly likes 4 minus, it's sharing 8 electrons. Whoops. 0 lone pairs sharing 8 electrons. So that does indeed equal 8, 0. So now oxygen, let's try this left side first. It'd be 6 minus, okay, just to make sure I'm doing the math right. 6 minus, it has 4 lone pairs, plus 4 over 2 because it's sharing 2 there, also equals 0. Okay, and now for the oxygen with the hydrogen, it's going to be 6 minus 4 lone pairs, and it is sharing 4 electrons, so it's also going to be 0. The hydrogen, I'm specifically doing that oxygen in the corner last, and you'll see why. Okay, so the hydrogen is 1 minus, okay, sharing 2 of them, so it does equal 0 as well. Now for the last oxygen, we have 6 minus, okay, it actually has 6 lone pairs plus sharing just 1, well, 2 electrons. That's going to be a minus 1, and there is where our negative is going to be, right there. So this and the whole thing is minus 1, but exactly this is going to be our Lewis structure for HCO3. Let's see how we did. Well, HCO3 minus, specifically one of the oxygens is going to have that negative charge, and everything else is neutralized, and the hydrogen is actually sticking on the oxygen, not the carbon. Wow, we did it. Yep, and a double bond right there. Ooh, nice, we have it all. So double bond, one of the oxygens has the hydrogen, and then that's what the negativity is. So this is correct. I always get a little bit scared because it's hard to notice double bonds, but exactly, we have 4 electrons being shared right there, so that exactly is what the double bond is. Okay, that's correct. Now move on to the last question for today, question 30. Okay, why does NH3 have a lower boiling point than H2O? So why does NH3 have lower boiling point than H2O? So let's actually quickly draw the Lewis diagrams. We're not going to go through some of the questions asking. I'm just going to draw it out, simply put, and we have solved NH3 already. Okay, and H2O. Okay, so with this being said though, okay, it's kind of tricky at first glance to understand why, but in terms of the lone pairs, that does play a role in it. Now for this, the reason why NH3 have a lower boiling point is because, yes, actually I would say that this part I don't agree with. That second part says that it has twice the hydrogen bonds than NH3. Every bond with that nitrogen has with hydrogen, that's a hydrogen bond. So all these are hydrogen bonds because they're all with N. So that has 3 hydrogen bonds, right? And water has only 2 hydrogen bonds. In fact, I'll actually see what they're saying, because maybe they're on something. So how many hydrogen bonds are in NH3? Ammonia can form 2 hydrogen bonds, not 1. Now I'm more confused. Ammonia has a capability for 4 hydrogen bonds. I'm just gonna stick with my answer because 3 is between 4 and 2. So I wouldn't just look at the hydrogen bonds. Actually, I would look at actually how hard both water and nitrogen want to fight for keeping their hydrogen bond. So let's say this hydrogen wants to leave, right, to form OH minus, okay, which it does. That it's something that water really will struggle against. because it doesn't have many hydrogens. It wants to have as many hydrogen bonds as possible while still keeping its its electron charge is 0, right? Because right now it's at 0. So they're fairly similar, but the difference is that water it's a bigger impact for it to lose. Water losing one hydrogen bond, meaning that now it only has one left. Nitrogen, the way I see it, is that it has 3 hydrogen bonds, so losing one isn't as energy draining compared to water, because exactly like it's losing a hydrogen in worst case scenario, just so that way it can be like NH2 minus, but it still has at least those hydrogen bonds, those other 2, to kind of buffer it. But point being though is that I think that I mean, the answer they have is definitely correct, but I would say it's more so because oxygen, to lose a whole hydrogen just takes more energy because there's less of it to spare. That's the way I'd put it. And also the other thing you can use as well, actually, go to the periodic table. Okay, nitrogen electronegativity is 3.04, oxygen is 3.44. okay, each bond with hydrogen, okay, is stronger for oxygen than nitrogen because there's a higher electronegative difference. So because of that, water, that's a very polar covalent bond that water does not want to really get rid of, hence why the hydrogen bonds are stronger there as well. So if anything, I'll refer to electronegativity to kind of determine that, but nonetheless this is correct. So yeah, that's why NH3 has a lower boiling point, because for one, oxygen has more to lose technically because it only has 2 hydrogens to begin with, and 2, the electronegative difference between oxygen and hydrogen is greater than the electronegative difference between nitrogen and hydrogen. Okay, I wouldn't really talk about the shape, because although oxygen is bent like that and nitrogen is kind of like this, I wouldn't really know specifically how shape plays into the actual a stronger bond. But overall though, I do agree that H2O has a higher boiling point, and that's one of the reasons why. So I'm gonna mark this as correct, because we may just be arguing semantics. We may actually end up being saying the same thing, but I'm approaching a different method. But I would just actually put make sure to mention electronegativity difference as well. So yeah, that was the last question for this session. So I just want to thank you again for joining me this morning. I hope you have a wonderful rest of your day, and yeah, enjoy your weekend, enjoy your Saturday, go out, have fun. If you want more help when it comes to these type of chemistry questions, definitely check out the links in the description below. Book a time with one of our tutors here, and just really get familiar with these concepts. Thanks again, and have a great rest of your day.